Today's lesson we're going to look at changes in matter and energy, and we're also going to focus towards, well, in the middle, actually calculating heat problems. So let's look at a few things here. So we already know what chemistry is, right? Chemistry is the study of matter and its transformations, right? And so when we're talking about transformations, we're really referring to either physical or chemical or even nuclear changes. So physical changes, you know, changes in state, right? Looking at something transferring from a solid to a liquid to a gas. In a chemical, you're looking at any type of chemical reaction, right? Synthesis, decomposition, double displacement, reactions like that. Okay, and finally nuclear reactions, when we're looking at actual, you know, nuclear reaction in the form of nuclear fusion, nuclear fission, alpha decay, beta particle decay, problems such as that. Now, we're going to be looking at thermochemistry, right? And so thermochemistry is the study of the energy changes that actually accompany these transformations. So whenever you have a physical change or a chemical change or a nuclear change, you're going to actually have some kind of change in energy. As we're going to find out, this change in energy is what we're going to know as the change in enthalpy. So let's look at the law of conservation of energy. It states that the total energy of the universe is constant, which means that the energy can neither be created nor can it be destroyed, right? So what happens is you're going to start off with a bunch of potential energy, and that potential energy eventually has the potential to do work. And what kind of work, right? In the form of some kind of, maybe some kind of kinetic energy, right? Where we have the ability to have atoms move, right, and increase in what we call a kinetic energy, right? So if we look at something like a solid, you know, going from a solid to, let's say, to a liquid, right? So solid to a liquid, right? We have the potential to do, to actually have these particles actually move. Right, so in order to get this potential, in order to get this kinetic energy, we need to really add heat, right? So if we add heat to this solid, right, we're going to get the particles to move a lot more rapidly, increasing in what we call the kinetic energy. Okay, kinetic energy. Now, energy can be transferred from one substance to another. It can also be converted into various forms. And as we said, the potential energy to kinetic energy, it's being converted pretty much, let's say, from one area to another, right? So we're not destroying it, it's just moving to a different spot. Now, hydrogen may undergo physical, chemical, or even nuclear changes. So if we're looking at a physical change for hydrogen, here's an example. Hydrogen liquid, okay, evaporating into a gas. So hydrogen boils at minus 252 degrees Celsius. This is just an example. You don't have to memorize it. But here's an example of a physical change. Notice the property of hydrogen gas doesn't really change, or sorry, hydrogen liquid doesn't really change. It just converts into a different state, and that state being a gas. Now, a chemical change of hydrogen can be as follows. Hydrogen can burn in the presence of oxygen to produce water. And this is an example of hydrogen burning, being burned as a fuel in the space shuttle's main engines. So what we have is hydrogen gas, okay, burning in the presence of oxygen to form a liquid. So notice the composition of this H2 actually forms a completely new substance. Okay, so that hence a chemical change. And finally, a nuclear change, something that actually occurs in the sun, where actually hydrogen undergoes nuclear fusion in the sun, producing helium. Now, in some reactions, the energy released to the surroundings can be in the form of a thermal energy. And thermal energy is the form of kinetic energy that results from the motion of molecules. So movement of molecules, right? Kinetic energy. Anytime we're dealing with movement, we're looking at movement in the form of a kinetic energy being as a result of it, right? So kinetic energy resulting in movement of something. So here's an example. Ethylene burning in oxygen. So we've got ethylene burning in the presence of oxygen. Okay, so a combustion, complete combustion reaction. And what is it forming? It's forming some kind of energy as a result. So it's releasing an energy. And this is what we're going to refer to as exothermic. So here's a hint, a term that you've seen before, right? Exothermic. So anytime you have energy on the product side, right, as we have here, this is considered an exothermic reaction. It means energy is actually being released from this system into its surroundings. And we're going to talk a little more about system and surroundings in a second. So, when looking at the transfer of energy, we need to distinguish between the substances undergoing a change called a chemical system, right? And this is our chemical system, our equation, so to speak, and the system's environment, which is considered the surroundings. So, the chemical system is the reaction itself, right? The surroundings is pretty much where is this energy going, right? Or maybe is that energy coming from the surroundings into the system? Right, so a system often represented by the chemical equation, as we have right here. And the surroundings in this reaction would include anything that would absorb the thermal energy that is being released from this reaction. So where is this energy going to? Where is it being released? It's being released into the surroundings. And so what is the surroundings? Is whatever gets exposed to this energy. Now, when the reaction occurs, heat, right, we're going to use as a letter Q, is actually transferred between substances. So we've got energy that is required to break bonds, right, in a compound, as well as the energy that is being released when new bonds are formed, right? And that's something that you should have covered in previous lessons. And if you go into my lessons on solutions, we kind of talk about the idea that the energy input, right? The energy input in a reaction, right? So input of energy is required to break the substances in the reactants, right, of a chemical equation. And then it's going to form products, and those products are going to be part of the output of energy. So the energy that is formed when we put together our new products, right? And that would be released. So it depends on which one requires more energy. Is there more energy in the input, or is there more energy in the output, right? So is there, and that's really what's being looked at in terms of, is more energy being required, or is there more energy being released into the surroundings? So heat refers to the transfer of kinetic energy from pretty much the reactants forming our products. So heat is expressed in the same units as energy, and we're going to use the units of joules, which we use as capital J. And just keep in mind, if we are making any conversions with kilojoules, 1 kilojoule is equal to 1,000 joules, but you should already know that. Now, when heat transfers between a system and its surroundings, measurement of the temperature of the surroundings are used to classify the change as exothermic or as endothermic. So endothermic energy being required for this reaction to take place. Exothermic meaning to exit. So energy being released into the surroundings. So endothermic means energy into the system. Exothermic, energy out into the surroundings. So exothermic changes, again, just to kind of reiterate, energy is released from the system, usually causing an increase in the temperature of the surroundings, right? Because you're all of a sudden increasing the amount of energy, you're increasing the amount of heat, so to speak. Endothermic changes. Energy is absorbed by the system, usually causing a decrease in the temperature of the surroundings. So heat is coming in, or should we say, an energy is coming into the system in order to allow for this reaction to actually take place. So let's look at the reactants and products. So bonds are broken in the reactants, bonds are made in the product. So new bonds are made. So now, if the energy that is absorbed is greater than the energy that is being released, we have what we call an endothermic reaction. It means that the system absorbs the energy that's required to actually break these bonds, and the bonds that are actually being made release very little energy. So in fact, there is more energy that is actually being is required to break these bonds than they are to actually make the bonds, right? So that's what we are looking at in terms of right. So remember, when bonds are made, energy is released, but the energy is little with respect to the amount of energy that is required to break the bonds. Okay. Now, if bonds are broken, right, as they are in reactants, and when bonds are made, if the energy absorbed is actually less than the energy that is being released, this is considered an exothermic reaction. It means the system releases energy. So what happens is very little energy is being absorbed to break these bonds. So really easy to break these bonds, but we have a lot more energy is being released, so that so the amount, if we look at the change in this energy, right, the energy that's coming in and the energy going out, there is a lot more energy that is going out of the system into the surroundings, will result in what we call an exothermic reaction. So when you close the door at your home on a cold day to prevent the cold from getting in, you're actually preventing the heat from escaping. That's really what's happening. So you're preventing the kinetic energy in your warm home from transferring to a colder object, right? Which includes the cold air that is outside. So you close the door because you don't want to let the heat out, right? That's really where it's going to go. That's really where it really wants to escape to. So let's look at some different chemical systems. We're not going to talk too much about these right now. We are going to focus a little more on these systems later on. An open system is one in which both matter and energy can move in and out of the system, right? It's open. So using a beaker, right? Energy can easily come in, matter can go out, right? Energy can go out, right? Because the beaker is completely open. Isolated system, an ideal system in which neither matter nor energy can move in or can move out. It's theoretical, but it doesn't really exist. Okay. And then finally, a closed system, one in which energy can move in or out, but not matter. So energy can be released, energy can come in, but matter will remain within this so-called closed system. So, measuring energy changes, calorimeter. A calorimeter is a technological process of measuring energy changes in a chemical system. Okay. Now, one really simple calorimeter that we can actually create is with polystyrene cups. So you get a cup, polystyrene cup, and you seal it, right? So two of them, seal it, one over the other, and stick a thermometer through it. So it almost looks like a drink here. So you stick your thermometer through it as a standard, really simple calorimeter that can be used, right? To do some simple changes, chemical changes. You can actually do measure the energy changes of changes in state, right? So if you want to put water in here and let it in room temperature and monitor it, it's something you can actually use and actually do and make such calculations. But anyway, let's look at the quantity of heat, which is Q transferred, is represented by the following equation. Q is equal to mc delta T, and this delta represents change in, right? So what's the delta part? Delta T, so change in T, which is temperature, right? Another way of writing that is in brackets TF, so the final temperature subtracted by the initial temperature. So what is the final temperature resulting? So if the temperature is increasing, right, the amount of energy is going to be a positive value. If the final temperature is a lower temperature, of course the amount of energy is going to be negative. But we'll worry about that when we actually deal with some actual problems. So let's look at what these letters represent. So Q is the heat transfer, right? And note Q, we're going to be using joules. Mass, right, is our M. Mass is in grams, right? So these units really important to want to use for the sake of this following, this specific heat capacity. This here is going to be pretty much given. Okay, so if you look in your textbook, you may have a table that you may be referring to find specific heat capacity. Notice the units are in joules per gram of degrees Celsius, right? And if you look at it, right, you can cancel out, right? Notice here, mass is in grams. So grams here, right, everything after the joules per, these are part of the denominator. So what's going to happen is grams is actually going to cancel out with the grams for mass. Degrees Celsius is going to cancel out with the temperature degrees Celsius, which will leave us with joules as our units of energy, which is really, if we're trying to find the heat transfer, that Q is in joules, as we said. Okay, and finally, delta T is a change in temperature. We're going to use degrees Celsius. Most of the questions you're going to use degrees Celsius. You may use Kelvin, but again, with Kelvin, keep in mind that you are going to have to make some adjustments to your specific heat capacity to make sure that degrees Celsius is in Kelvin. Okay, same thing goes if your units, you know, if you're using kilograms, make sure you're converting kilograms to grams, or if you're given this, let's say you're given this, but it's given to you in kilojoules, make sure that you do make the conversion to joules. Now, specific heat capacity, just to really look at what does it mean. It means that the quantity of heat required to raise the temperature of a unit of mass usually is 1 gram of a substance to increase 1 gram of substance by 1 degree Celsius. So if I've got a gram of something, right, how much heat is required, how much energy is required to raise that 1 gram of that substance, to raise it by a temperature of 1 additional degree. So if a substance, if I've got 1 gram of a substance that's already let's say, I have at 20 degrees Celsius, to raise it to 21 degrees Celsius, how many joules of energy? So if you look at here, if we've got ice, and I want to raise ice, right, by 1 degree Celsius, I need to input this amount of heat into, or expose 1 gram of ice to this amount of heat in order to raise it by 1 degree Celsius. Sample problem. When 600.0 milliliters of water in an electric kettle is heated from 20 degrees Celsius to 85 degrees Celsius to make a cup of tea, how much heat flows into the water? So when we're looking at this, we want to identify pretty much what does this information give us. So right now here, 600.0 milliliters, that's how much water, that's the volume of water that we're putting into this electric kettle. It's heated. Temperature, initial temperature here is 20 degrees Celsius, and it's increasing to 85 degrees Celsius. It's asking us how much heat flow, right? So it's asking us for our Q. So we have Q is equal to MC delta T. Now, we know our delta T. We know our C value. Our C value is a given. So our teacher needs to give it to us, or they'll give us a list, or some kind of a table, some kind of reference that we're going to refer to. I would never ask my students to memorize specific heat capacities. So, obviously, we do not know our M value, and we do not know our Q value. And in fact, this is really what we're trying to find, which means somehow in this question, I must be able to calculate my mass using the numbers that I'm given. And the only thing that I'm really given here is this volume. So let's look at some of our givens. Always start off with our givens. So we've got our volume, which is 600.0 milliliters, but it's not useful to us in this equation. Our Q is, which is our really, in fact, what we're really trying to find. So really, this mass is also what we're trying to find, but this is the step that we need to do before we actually start. So we've got our C value here for our water, right, which is our given. And our delta T is 85 degrees Celsius subtracted by 20 degrees Celsius, which will give us a total of 65 degrees Celsius. Now, what we need to know is, to get the mass, right, think of density. Density is equal to mass over volume. We're given a volume, right, but we do not know the mass. That's what we're trying to find. But if we know anything about water, right, we know that the density, okay, the density of H2O, right, is 1.00 grams per milliliter. So we know that our density is equal to 1 gram for every 1 milliliter, right? So in other words, if we are trying to convert 600 milliliters 2 grams using this density of water, right? So what we're doing is we're going to isolate for M. So we're going to bring V over to this side of the equation, and we're left with mass is equal to density multiplied by volume. So we've got 1.00 grams per milliliter multiplied by 600 milliliters. I'm not going to put the to the exact number of significant digits when I'm doing my problems, just to kind of simplify some of the steps. So we've got mass is going to equal to, well, here milliliters is going to cancel out, so 600 milliliters is equivalent to 600 grams. So our mass now is 600 grams. So now what we're going to do is substitute into this equation Q is equal to MC delta T. So Q, we don't know what it is. M, we do know. M is 600 grams, right? Our C value, 4.18 joules per grams degrees Celsius, right? This dot here represents multiplied, so grams multiplied by degrees Celsius, which is multiplied now by our delta T, which is 65 degrees Celsius. Now, what's important to, and I tell my students to try to keep their units going, because the units are to cancel themselves out. So we've got grams cancels out with grams, degrees Celsius cancels out with degrees Celsius. The only set of units that I'm left with is joules. So when I multiply all that together, right, I'm going to get 163,000 joules is the amount of heat that is actually going to flow into the system. Now, I can leave my answer as that, right? Now, the thing is, you want to look at significant digits. 3 significant digits is the least number in our question. We've got 3 significant digits in our answer, so we can leave this as such. We can convert this to scientific notation. So 1.63 times 10 to the power of 5 joules, right? Also, again, 3 significant digits. Or if we want, it's up to us. It depends on if the question asks you to convert joules to kilojoules, which will give us 163 kilojoules. Okay, so therefore, how much heat flows into the water? Well, 163 kilojoules, or 1.63 times 10 to the power of 5 joules of heat flows into the water. Next sample problem. What would the final temperature be if 250.0 joules of heat were transferred into 10.0 grams of methanol initially at 20.0 degrees Celsius? So let's identify what are some of our givens. So question says, what would the final temperature be? So we know that TF is something we're going to need to find. This is going to be our unknown, right? 250.0 joules, right? This is our Q, the amount of heat required to transfer 10.0 grams, which is going to be our M value of methanol. So you'd have to look up methanol and the specific heat capacity of methanol. Find your C value. Teacher would give it to you. There might be a table in your textbook that will help you, will guide you along the way. to find the specific heat capacity of methanol. And finally, 20.0 degrees Celsius. This is our initial temperature. So let's look at our given now, just list them out. And so what we have here, our Q, 250 joules, mass, 10 grams, our specific heat capacity of methanol, 2.918 joules per grams degrees Celsius, right? Again, like I said, this is our given. And now the thing to be careful here with is our delta T is equal to TF minus our TI, right? Our final temperature subtracted by our initial temperature. And so what's going to happen here is really our unknown is within this TF minus TI. So what I'm going to do is I'm going to start off with the equation. Q is equal to MC delta T. My advice is rearrange the equation, right, first. So rearrange these letters. So what we want is we want to isolate for delta T. It's on this side of the equal sign. So what I'm going to do is I'm going to keep it on this side of the equal sign, and it's going to equal C. I want to get rid of this MC, but because the function between MC and this delta T is multiplication, when I move it across the equal sign, it becomes division. So I'm going to be dividing Q by MC. So now what I'm going to probably be doing next is substituting numbers into each one of these letters. So instead of Q, I am going to put in what the value of Q is. So 250 joules. I'm not going to put in the 0.0. Now, the thing to keep in mind, though, remember that your least number of significant digits in your question, depending on the function, right? If you're multiplying or dividing, it'll be based on the least number of significant digits. So you can ignore these 0.0s just for argument's sake in your problem solving, but remember to go back to those significant digits or decimal places depending on whatever is your final function. So we've got mass, which is 10 grams, right, multiplied by my C value, which is 2.918 joules per gram degrees Celsius, equals to delta T. And our delta T we've broken down to being TF, right, our final temperature, subtracted by 20 degrees Celsius. So what we're going to see here is ultimately joules is going to cancel out, grams is going to cancel out, and our final units obviously is going to have to be degrees Celsius, because, well, that's what's going to what we're going to actually get. So when we actually do this calculation here, right, when we're going to do this calculation here, 250, this is what I'm going to do first. I'm going to do this part here of the equal sign first, and I'm going to get 8.57 degrees Celsius is going to equal to TF minus 20 degrees Celsius. Now, thing to keep in mind, though, we are when we're doing this is such a calculation, what we're going to be doing, what we're going to be seeing now is, well, this part here, this 8.57 degrees Celsius is what we get here, right? So we're going to multiply these two. This will be our denominator divided by that, right? Which will give me this. So now what I'm going to do is I want to isolate for TF. So TF is going to stay, and we're going to get rid of this negative, or this minus 20 degrees Celsius. We're going to bring it over on this side. When we do, it becomes plus 20 degrees Celsius. So TF is going to equal to 8 point, let me redo that. My tablet's acting up. 8.57 degrees Celsius. I'm going to add it to 20. I'm going to put in my 0.0 degrees Celsius because that's really what we've got. Keep in mind now, because the final function is addition, it is based on the least number of decimal places in my question. Least number of decimal places in my question is 1 decimal place. So I'm going to make sure that my answer is going to also have 1 decimal place. So TF is actually going to equal 28.57 0.57 degrees Celsius. But I only want 1 decimal place, right? Because 1 decimal place is my least number of significant digits. So I'm going to look at the number I'm going to ignore, and my final temperature is going to equal to 28.6 degrees Celsius. So therefore, the final temperature for this heat question would be 28.6 degrees Celsius for methanol. Heat transfer and enthalpy change. Chemical systems have many different forms of energy, both kinetic and potential. So potential, the ability to do work. Kinetic energy is pretty much the actual movement of these of the energy, right? So in terms of kinetic energies, what are we talking about? They really include the following: moving electrons within the atom, right? The vibration of atoms connected by chemical bonds, right? So the movement of particles, right? And finally, the rotation and translation of molecules that are made up of these atoms. So when we're talking about rotational, translational, we are talking about movement of particles in terms of solids, liquids, gases, so to speak, right? So all of this deals with movement, right? Now, more importantly, when we're looking at potential energy, we're talking about potential energy in terms of nuclear reactions, right? So the nuclear aspect of the atom. So the protons, the neutrons of an atomic nucleus, as well as the electric potential energy of atoms that are connected by these chemical bonds, right? But don't worry too much about that. Really, we're going to kind of, this is more the theory aspect of this, but just know that when we're dealing with potential energy, you know, matter has the ability to move. It has the potential to do work, right? So the minute that potential starts to do work, starts to do movement, the kinetic energy is going to start to increase while the potential energy is going to start to decrease. So the heat content of a chemical system is referred to as enthalpy. Researchers have not yet found a way to measure the sum of all these kinetic and potential energies of a system. Okay, so what we have here is the reason for chemists to study enthalpy change, or the energy absorbed from or released from the surroundings when a system changes from reactants to products, but it's at a constant temperature, or sorry, a constant pressure. So constant pressure, is energy going to be released? Is it going to be absorbed from the system into the surroundings, and vice versa? And enthalpy change, we're going to use the symbol delta H, is the difference in enthalpies of reactants and products during a change. So what we have here is the enthalpy change, delta H, which is really the enthalpy, right, the heat content of the product subtracted by the heat content of the reactants. And we're looking at the overall enthalpy change of a system. It's equal to pretty much the heat of its surroundings. Okay, and we're going to talk a little more about that in the next video when we're looking at molar enthalpies. So, enthalpy change of a system equals the quantity of heat that flows from a system to its surroundings, or the surroundings to the system. Right? So really what we're looking at is, in terms of enthalpy change, we want to know, is something endothermic, so energy required, a lot of energy required, or is it exothermic, in which energy is being released into the surroundings? So the idea is consistent with the law of conservation of energy, that energy may be converted from one form to another, or transferred from one set of molecules to another, right? So it's being transferred from the molecules of the reactants to the molecules of the products. But the total energy of the system, of the surroundings, is going to remain the same, right? And that's that whole idea of the change in enthalpy is equal to the heat of the surroundings. Okay, so here's an example of an exothermic change here with this graph, right? This change from, so what we have here is we've got a high potential energy. So if we've got a high potential energy, we're going to have a low kinetic energy. But now, as the potential energy starts to decrease, kinetic energy is going to increase. Okay, but that difference, right? That difference is going to be exactly the same. Okay, so the change in potential energy of the system, delta H, equals the change in the kinetic energy of the surroundings, which is Q. So delta H represents the potential energy of the system. Q represents the heat of the surroundings, right? And this being consistent with what we said about the law of conservation of energy. That energy is not going to be created nor is it going to be destroyed. In fact, energy is just going to be transferred from one system to another. Okay. So energy changes in chemical systems are measured at standard conditions of temperature and pressure, such as SATP, before and after the reaction. So if you're stuck with understanding what SATP is, standard ambient temperature and pressure, please go back to my gas law unit where we kind of address the SATP and STP. So now, under such conditions, the enthalpy change of a chemical system is the change in the chemical potential energy of the system, because the kinetic energies of the system's molecules remain constant for now. All right, we're going to look at it in future videos. Okay. Now, we can observe enthalpy changes during phase changes, chemical reactions, or nuclear reactions. So when we're talking about phase changes, we're really talking about physical changes, right? So a change in state. So a gas condensing into a liquid freezing into a solid. So let's look at some types of enthalpy changes with respect to physical changes, right? Changes in state. So energy is used to overcome or allow intermolecular forces to act. Fundamental particles remain unchanged in a molecular level, right? So if we've got here at a molecular level H2O is still H2O in the end result. The only difference is pretty much is the fact that really heat is being either released or heat is being it needs to be input for this reaction, let's say, to take place. So if we look at this example here of water, right? Of water pretty much subliming, and it's under what is subliming. It's undergoing sublimation, right? Because it's going straight from a gas straight to a solid without that liquid state in between. So when it does that, heat is actually being released, right? Because remember, for a gas to go down to a solid, the kinetic energy has to decrease, right? Kinetic energy of these particles need to decrease, right? Because that is, in order to solidify. Now, temperature changes during dissolving of pure solutes, right? So here's an example of us going from a solid potassium chloride to an aqueous, right? We're putting this, we're dissolving this in water, is going to require an input of heat, right? So all of a sudden, this is considered an endothermic reaction. Right. Now, typical enthalpy changes range in the following. So our delta H can be anywhere from 1 kilojoule per mole, okay, kilojoule per mole, to 100 kilojoules per mole. Okay, and that's a typical one for physical changes. So it's very low, right? So enthalpy changes in physical changes is considered very low. Now, enthalpy changes in chemical changes, right? Energy changes overcome the electronic structure and chemical bonds within the particles, right? So all of a sudden, the reactants, right? The molecules that make up the reactants have to break apart, right? Those bonds need to break. So what we have here in this combustion of propane here, or in this calcium here reacting with water here, in this propane, all of a sudden this C3H8 has to break apart. It's reacting with oxygen, and these oxygen molecules also have to break apart. So the energy that is required to break these apart and restructure to two completely different products, what's going to happen is heat is actually being released. So what happens is less energy is involved to break these bonds together, but a lot more energy is actually being released when these bonds actually form, right? And the same thing goes with this reaction of calcium plus water, right? This water molecule has to break apart, right, and form this hydrogen gas And again, a lot more energy. So again, another exothermic. As we said, when we see heat or energy on this side of the reaction side, we know it's considered an exothermic reaction. And typical enthalpy changes greater than those in a physical change can be anywhere from 10 to the power of 2 to 10 to the power of 4 kilojoules per mole. Okay, and even higher than that are the nuclear changes. So a lot more change in enthalpy is found in typical nuclear reactions, right? Energy changes have to overcome the forces between the protons and neutrons in the nucleus, right, of an actual atom. So new atoms are actually going to form, right, with a different number of protons, different number of neutrons. So all of a sudden we're converting this uranium. So this uranium is undergoing a nuclear decay and is pretty much releasing a helium proton, and at the same time it is releasing heat, right, exothermic. So the enthalpy changes is pretty much a lot greater, and notice here how much greater. A lot more energy is available. So there's a lot more energy, right? That change in enthalpy is greater at the nuclear state.